Hello, my name is Nicholas, and I wanted to present this work we developed for MECOM 2025 at HCS, which is called a novel physically based interpolation method for bathymetric data. I mean, at HCS we do a lot of river modeling, typically in 2D, and anybody that has performed this type of modeling knows that having an accurate bathymetry is very, very important because it's the most influential parameter you can put in your model. This is true when you do hydrodynamic simulations, but it's even more true if you do morphodynamic modeling or sediment transport of any sort. In practice, survey data comes to us typically as a set of points, X, Y, Z, that are usually aligned with a set of transects in the river, but never actually cover the entire domain. So typically, to get to your 2D mesh, you need to interpolate the data somehow using some method. A number of methods exist to do that, but most often people use like typical general purpose methods, such as inverse distance weighting or TINs. These methods use purely geometrical relationships and do not have any notion of hydraulic principles, let's say. So when you apply them to river bathymetries, you typically get a lot of unrealistic features, such as peaks, ridges, and discontinuous flow pathways. And besides that, these methods do not work very well if you try to extrapolate beyond the points you already have, so their capacity for extrapolation is very limited. This is an example of how this method looks for a typical case. This is actually one of our practical cases. So we had all these surveys here on the left. You see, many of them were quite well structured in the transects of the river, but some of the data was a bit more disorderly, let's say. And when you apply inverse distance weighting with typical parameters, you get something like this. These are the peaks I was talking about. These were the ridges. So typically a lot of noise and very discontinuous bathymetric field. If to the same data you apply the triangular mesh, you get something like this, which works much better in general, but still presents some artifacts, some discontinuities here and here, especially anywhere where the data is not as orderly as in the other parts. There are other specific methods for bathymetry, such as trying to construct cross-sections from this point data and then interpolate longitudinally in real ridges. This is something that's done very often as well, but it's a very artistic job, and it works well for single ridges like this, but if you get a bifurcation like this or a confluence, then it's much more difficult to apply, because what profiles would you interpolate to cover this zone, right? So in this paper we proposed a new method, a physically based interpolation algorithm that uses hydrodynamic principles as an organizing mechanism to spread the bathymetry across the domain. And we do that by combining the numerical solution for the shallow water equations with a diffusion-based interpolation equation. This diffusion equation basically spreads the data following the velocity field, so it tends to be much smoother and captures more realistically the flow structures in the river. This method we are calling velocity-based diffusion, or VBD interpolation. Basically, this works like this. We have an initial bathymetry, which can be very simple, such as just a constant value throughout the domain. We first solve the shallow water equations with that bathymetry. We then get a tentative velocity field, and we use that velocity field to compute the diffusivity field. That diffusivity field, which I will explain in a minute, is used in the diffusion equation to interpolate the bathymetries, or to spread the bathymetric data throughout the domain, which leads to a new bathymetry, a new field of bottom elevations. Then we can iterate this methodology using this new bathymetry to solve the shallow water equations again, and we repeat the process a number of times until we get convergence. Typically this happens quite fast, so 2-3 iterations it's probably enough, or at least it was enough for our tests, and you get a final bathymetry which you can then use for your main modeling studies, let's say. About the equations, very quickly, the shallow water equations, it's very well known. There's not much to say here. We have a continuity and a momentum equation. We are solving these equations directly using an open source solver, in this case Telemac, so there's not much to discuss about this. The diffusion equation that does the interpolation is a bit more unique. So here the variable we are solving for is ZB, which is the bottom elevation. And basically we are evolving it over time following a diffusion term. So how does this work? If you put any initial bathymetry and you diffuse it over time, what you will get is a smoother version of it. So it will get smoother and smoother over time. Of course, we don't want our bathymetry to just be smooth, but we also want it to follow the surveys that were measured in the river. And we do that by incorporating a source term here, S, which basically forces the solution of the equation, the bottom field, the bottom elevation field, to be equal to the surveys, or at least very close to it. However, this source term is not active in every cell of the model, but it's just active on the cells that actually contain a survey point. So basically, we are using the diffusion equation to smooth the solution, but we are still forcing it to go through all the measurements, let's say. And this diffusion we are applying is not a simple isotropic diffusion, constant in every direction, but instead is anisotropic. It's the tensor. So we create a tensor with two principal directions. The first one aligned with the velocity field, and the other one transversal to it. And in both directions, in absence of velocities, we apply the same diffusion A. So if there's no velocity, then the diffusion is just uniform, isotropic in every direction. But if we do have a velocity, we add a second term to that longitudinal diffusion component, which basically is much stronger than the transversal one and forces the bathymetry to be spread predominantly in the direction of the flow. This model has three parameters, which are these A, V parameters, and then K, which was the source term in the previous slide. We found this set of, we tested different set of values, and we found these ones to work very well for the tests with it on different reaches of the Paraguay River. But I think they are not yet very universal. I would say that the idea would be to adimensionalize these terms with some lengths and time scales of the river itself, or the river flow you are solving for, which I think would work much better in making these parameters more universal. But we haven't yet applied this to any other rivers, so we really don't know yet. A couple of details about the solver. So we programmed a custom solver in OpenFOAM called BATHYMETRIC, so because of diffusion of bathymetry. And this solver basically uses as boundary conditions in the banks. You need to specify a Dirichlet boundary condition, so to specify the bank elevation, which by definition should be around the same as the free surface elevation on the river. You can, if the reach is short, you can just impose constant values or uniform values in the entire reach. But if you have a longer reach, it's probably better to just impose a longitudinal profile. And then for the inlet and outlet boundary conditions, we use a Neumann zero normal gradient boundary condition. So the bathymetry of the surveyed in the inner part of the domain is naturally spread toward the boundaries. The diffusion equation is solved in transient mode until a conversion is found or a stationary solution is found. And a couple of numerical details. It is first very important to discretize the source term implicitly because it's a very strong term, and if not, the model becomes unstable. And it's also important to apply several non-orthogonal correctors to be able to properly compute these diffusive fields in the triangular mesh we are using. For the Laplacian, we are using this Gauss linear corrected scheme, which seems to work well. And a bit of thing to improve, let's say, in the future is that we are using the diffusion equations we are solving with OpenFOAM compute the bed elevations at the cell centers, while Telemac uses bed elevations on the nodes. So when we go back and forth between these two solvers, we need to interpolate one way or the other, and this interpolation adds extra diffusion that at some point you would like to remove from the process. But it was easier to use Telemac for the diffusion for the shallow water equations since we already had it, and programming a custom solver in OpenFOAM was also very easy. So for development purposes, I think this was the most easy route. A couple of applications. The first one is to this reach of the Rio Paraguay near Urbano. So it's a 12-kilometer reach with 2 southern surveyed points. We meshed it with a triangular mesh between 10 and 25 meters in length. We imposed a typical flow rate and typical levels, water levels on the downstream side. Also a level for the banks. And we applied 2 iterations of the method. And this is how results look in general. So you see that first we get a very smooth bathymetry throughout with very few artifacts. And also the method is extending without issue the surveyed bathymetries from this cross-section all the way up to the upstream side of the mole, which is this one more or less, without any issues. It does look very nice. And it's doing more or less the same on the opposite side. So it's interpolating very cleanly between these 2 last cross sections, and it's even predicting a zone with higher elevations or like a bank, which is present in the data because you have higher depths here and lower depth in the middle. So the model the process is interpolating very well between those 2. If you zoom in to that same place we were looking at before with the other methods, you see that indeed the interpolation is very smooth, and there are not any artifacts here at all. And it's handling very well this bifurcation here. If we compare this figure with the previous ones on the same reach, we also see that none of the artifacts present with the other 2 methods are to be seen here. The field looks much more smooth and more like friendly toward 2D modeling, I would say. Another place in which we applied with this method is in the Paraguay River downstream of Pilar. This is a different reach, 8 kilometers, 5 southern surveyed points. In this case, since we wanted more detail, we meshed with a finer mesh, 5 to 10 meters. We had to apply flow rates both in the main river and in this tributary, which is the Bermejo. And also applied some, we started from a constant bathymetry and we applied water levels, both to the outlet boundary condition and to the banks. And we used 3 iterations on the method. Once again, the method produces a very nice bathymetry field, although this is perhaps a bit less challenging case because it has a lot of surveys and they are very orderly. But I wanted to highlight in particular how well the method is handling this secondary channel here. This channel only has like a longitudinal profile along the center of it and just a couple of cross sections, and with that data it is handling the bathymetric very well. It's handling both the upstream and the downstream sides very well, and also this channel, this small pond here as well. The method can handle all type of things, even when you don't have a really definite flow there. It is also extending this last. There's only a small zone with higher depth there that the method is interpolating toward the boundary in the Bermejo. I don't think this is super accurate, perhaps, but in the absence of any data on this small reach of the tributary, I think that the results look very natural. So it's probably better having this thing than just some weird artifact here. Finally, another application, a much more ambitious one. This is a 500-kilometer reach in Brazil, also for the Paraguay River. It's going from 70 kilometers upstream of Ladario to the confluence with the Apa River, which is this one. This is a very long reach with 6 million surveyed points. So to make it faster, to interpolate the bathymetry, we split it in 7 sub-reaches. We meshed it with meshes from 20 to 25 meters in size, and we applied the the VBD method to all of these reaches separately. The only thing is that since this was a very long reach, we applied the bank elevations as longitudinal profiles instead of constant values to better capture how the banks are higher, let's say, the more upstream you go in the river. We got a field for the entire 700 kilometer reach, but I will just show you this sector because I think it's interesting. You can see that the main channel has many bathymetric points or many surveys, so the interpolations here is good, but you would expect this from many other methods as well. The key advantage of this new method is that it also generates feasible bathymetries for all the secondary branches that have very little data or even no data at all. Of course, I don't think this bathymetry in these unsurveyed branches, let's say, it's very accurate, but at least it's smooth, and in the absence of data, it's something that you could use in your model without a second thought, let's say. So it does create very nice bathymetric fields for your models, and it handles very well all these complexities, let's say, that other interpolation methods will struggle a lot with. Finally, a short performance analysis we've done. This is basically, the idea was to take one of the cases and split the data set into two. We use one part of the data set for the interpolation and the other part, a test data set, let's say, to compute errors with and evaluate the errors. Yes. So this is the case we picked. So the one I showed before. This is how it looked with 100% of data used for interpolation. But if you start decimating the data like this, 50-50, and then 10-90, so only 10% of the data remaining, you see that with that amount of data, the IDW interpolation and the TINs look awful, while this VBD method still looks very nice. It does not predict very accurately this zone anymore. It used to predict like higher levels here. Now it's giving more continuity between these two green parts, but that is because all the data that indicated higher elevations here is now missing, so the method cannot really know that it should create higher elevations there. But the rest, it looks very, very smooth, and it's handling this bifurcation very well. So, still, if we do like a quantitative analysis of the errors, we see that this VBD method gives you lower errors than both IDW and TIN for root mean square errors and also for mean average errors. But the improvement is not necessarily spectacular. Let's say it's a bit subtle. I still think the method it's preferable since it creates more model-friendly fields, let's say, so with much less artifacts, even though the precision is has not increased as much. Finally, for conclusions, we have presented a new physically based interpolations framework for river data that incorporates this hydrodynamic information through the solving of shallow water equations and then the usage to compute diffusivity and interpolate the bathymetry using a diffusion equation. This method is quite computationally expensive, much more than traditional techniques, but it does require very little to no manual labor, so it could save you a lot of money perhaps in practice. Actually, for that 700 kilometer reach I mentioned a little bit ago, all the calculations for the 7 sub-reaches in both the hydrodynamic and the diffusion equations and all the iterations in between took 8 hours on a single 24 course node. So it's not even that expensive, and it did require very little manual labor, so it actually saved us a lot of man hours. The quantitative performance analysis also showed improvements compared to IDW and TINs, which demonstrates that the method is a bit better than those in terms of accuracy. And for future work, I think that the first thing we should do is try to do a more universal calculations of those parameters, perhaps through a dimensionalization, as I said before. And I also think there is some room to add extra terms to these diffusion equations. Perhaps a term that pushes the bathymetry up when there are low velocities and pushes it down when there are higher velocities, let's say. So like a scour deposition term based on the velocity. I think that could help the interpolation method capture some features that perhaps were not very well surveyed using less data. But of course, probably with coefficients that might be like problem dependent. So it's something that should be researched well before using. So thank you very much, and I hope you get something useful out of this presentation.